Okay. Thanks for a nice day of talks, everyone. I'm Tom, and I'm a second-year PhD student in Antonio Del Rio Chinona's group at Imperial College London. And this work was done alongside Nosheen and Omar, who focus on the fluid dynamics, and Jonathan at the University of Newcastle, who has a group focusing on 3D printing. So we know that there's an increasing demand for efficient reactors within chemical engineering, and these will help support CO2 reductions that we require to reach net zero. This goes without saying. And in terms of looking at the history of reactors, they've obviously changed a lot throughout time. We have a reactor from the Haber-Bosch process at the top here, so one of the first reactors. And we're looking to increase the efficiency of these and really look into going to the next generation of chemical reactors. So as we're looking to manufacture things continuously and find more sustainable processes. And so this talk will be focused on mesoscale reactors. And mesoscale reactors lie somewhere between micro scale and traditional chemical reactors. So in the middle, I've tried to get as accurate as I can a real size on the screen. So that's about how tall a mesoscale reactor is here. And so a mesoscale reactor combines the properties of microscale reactors, such as good mixing performance and heat transfer, with higher throughput. And importantly, this class of reactor is made possible via additive manufacturing. So now we can 3D print these designs. This gives us the remit to open up the design space and specify higher dimensional problems and more complex designs. So I've just included a few down here. And so the resulting design problem, given that we're manufacturing these reactors using 3D printing, is computationally expensive. Gradient information is often unavailable. And as I said, we're dealing in high-dimensional and relatively complex design spaces. So this is our problem setting. And so what I'm going to talk about today is what we call algorithmic reactor design. So treating this effectively as an optimization problem, where we're looking to evaluate the performance of a reactor, select the next reactor to evaluate within our experiment or within our simulation, and converge on some solution. So specifically, I'll be outlining a framework for this kind of reactor design. Within this framework, we apply multiple fidelities to enable this optimization. So we have a very expensive optimization problem. We're going to deliberately do worse simulations in order to get a solution here. I'm going to outline some novel reactor parameterizations for the mesoscale, and we're going to investigate our optimal solutions. So again, just an outline here. I'll be going over the case study to begin with and our problem setting, then our solution approaches, and then finally, all the way at the end, our solutions and what we can learn. So here we're dealing with pulsed flow helical tube reactors. So these can be seen as a combination of a kind of traditional oscillatory baffled reactor as well as a coil tube reactor. And so what we have here is mixing. We don't have things like fouling and these are easier to clean than these oscillatory baffled reactors. So we know this class of reactor is good. The oscillatory flow induces Dean's vortices within the coil, and this promotes mixing radially, but inhibits mixing axially along the length of the reactor. But the questions we want to ask are, how do we get the best performance out of these reactors? Is the geometry a factor? Which geometries are best? And do the oscillatory conditions matter? Can we induce similar behavior without these conditions? So initially, I'm going to present a basic parameterization of trying to answer these questions. So this parameterization involves 3 geometry parameters: our coil pitch, our coil radius, and an inversion parameter which specifies a location along the coil that the coil inverts direction. We felt this might be interesting. And jointly, we're looking at parameterizing the operating conditions. So these are pulsed flow conditions, and we have available a frequency, an amplitude, and a velocity here. But then taking this idea and extending it one step further, I'm going to present what I'll call these extended parameterizations. So given the fact that we are 3D printing these reactors, let's really open up the design space and see what kind of things we can get. So on the left, I'm applying polar Gaussian processes at certain points along the coil, and these specify the cross-section. So these provide us with the ability to change the cross-section of a reactor. And secondly, I define points within cylindrical coordinates, and I apply some control parameters here, and this defines our coil path. And with both of these parameterizations, we've designed them in such a way that all our reactors are feasible within our design space. So with the path, we're actually looking at a deviation from a nominal coil, so we don't get any self-intersections. And likewise with the polar Gaussian processes, we define the bounds for our cross-section in such a way that we're guaranteed to get feasible reactors. And I mentioned this aspect at the beginning, but in order to evaluate these reactors, we're going to be performing simulations. And so I'd just like to outline some aspects regarding these simulations. So here we have two independent fidelities of a given simulation. So we have the axial fidelity, which defines the number of subdivisions of the mesh along the length of the reactor. And we also have the radial fidelity. So both of these things control the accuracy of our CFD simulations. And we're going to treat them as independent here. This is a small point about the fact that the joint space here is non-ordered. There's no way of saying which is more accurate than another, but we treat the highest fidelity as the element-wise combination here. So I've talked about the parameterizations. I've talked about the fidelities that we'll be applying. I'll just briefly outline the evaluation of a reactor. So we simulate an impulse tracer at the beginning of the coil. We induce the oscillatory boundary conditions using our parameters here. We solve the dynamic CFD problem, and we measure the concentration of the tracer at the outlet. And this is all done using PyFoam and OpenFoam integrated. So when we're evaluating these configurations, what we really care about here is our plug flow performance. So this is what we focus on in this study. So we have a residence time distribution that results from a simulation. We then fit a tanks in series model to this distribution, and we gain a single value, which is the equivalent number of tanks in series. And the higher this value is, the stronger the plug flow performance of our reactor, which is generally what we're interested in optimizing. Okay, so up to now, I've effectively outlined what's within our black box. So our black box now takes our parameters, which define a geometry. It takes two independent fidelities, and it gives us a reactor performance. So the question is, how do we solve this expensive black box optimization problem? Well, I've kind of provided a hint by the fact I've included the fidelities here already. But I'll just outline expensive black box optimization problems. So there are a number of ways of solving these. There are direct approaches where we're just using single function evaluations to decide which set of inputs to evaluate next. So this would be like just choosing the next reactor based off the previous ones. But there are also model-based approaches. So it goes without saying one of the most prevalent model-based approaches is Bayesian optimization, where we're choosing our next reactor geometry based on an expected objective value, but also an expected variance. So we're managing exploration and exploitation in our search space here. So this is really what we have. We have the ability to balance exploration and exploitation. But now we have these fidelities that we could play with. So we have an additional sort of design parameter, which controls our information with our cost. And so here we're looking to apply lower fidelity simulations throughout optimization to help us reach a solution. We know these are going to be lacking in information, but we're going to show how we correlate this information to learn about higher fidelity simulations. So we have an extra thing to play around with here. just a brief overview of what we've done previously. So previously we tried to apply, or well, we did apply deep Gaussian processes as a multi-fidelity model. So this can be seen as an extension of a sequential multi-fidelity model. I'm mainly going to outline the downsides. It limits us to a single discrete fidelity parameter, which scales poorly with a number of discrete fidelities. Training deep Gaussian processes is not yet a robust procedure. Can be time-consuming depending on the implementation. And we can't model the cost of a simulation as a function of our inputs. And this is something that I neglected to mention earlier on. But importantly, within our simulation, our cost of a simulation isn't just a function of our fidelities, but it's a function of our inputs, for example, pulse flow operating conditions as well. So, deep Gaussian processes are in theory a good multi-fidelity model, however in practice, not so much. So what do? Well, we're going to model our input parameters and our fidelity parameters in a joint space, in a single Gaussian process. And this means we're making the assumption that our fidelities are continuous, but it allows us to model continuous fidelities, and it allows us to model multiple independent fidelity parameters. So, we have a Gaussian process that models our objective function as a function of our inputs and our fidelities, and we also specify a Gaussian process that models our cost of a simulation as a function of our inputs and our fidelities. And we construct an acquisition function that balances the information gain from an evaluation with the cost of a simulation. So what I'm showing here is that we're maximizing our information. Z bullet here is the highest fidelity, I should say. So we're maxing the expected information of our highest fidelity, but we're weighting this by the cost of a simulation at the fidelity that we're evaluating at, and we're including an information loss term which characterizes how much information we're losing by evaluating at a lower fidelity. So this is the problem we're going to solve at each iteration to decide the next set of inputs and our next simulation fidelities. Okay, so going on to some results. First of all, we had to validate that our fidelities did in fact vary continuously, and therefore we could model them within a Gaussian process. So we performed an experiment where we measured the residence time distribution of a reactor in real life, and we performed a number of simulations at increasing fidelities, and we showed that the value of tanks in series that we obtained from the simulation tended towards the experimental value. So we took this as a sign that we could model our fidelities continuously. And this is really a slide demonstrating the convergence of the algorithm. Now, I should say that simulations performed at lower fidelities are biased than simulations performed at higher fidelities. So it's difficult to make a like-for-like comparison. It's difficult to figure out if these types of algorithms are converging. But what I'd like to get across is on the left-hand side, I'm showing the iteration of our algorithm, and on the bottom, I'm showing the time. And you can just see the impact of performing these lower fidelity simulations is quite significant within the optimization here. On the right here, I've performed dimensionality reduction just in the input space, so just the geometry parameters. This area on the right here indicates our initial design of experiments, our static design of experiments. And we can sort of show that our parameters are varying in a systematic way. They're varying here, but you can glean a number of insights from these types of plots. Here are the fidelities evaluated throughout our methodology. So on the top, I'm showing the cost of a simulation, the average cost at both the radial and the axial fidelity value. And on the bottom, I'm showing the number of times it's evaluated. The cost is non-smooth in this axis because, as I mentioned earlier, the cost is actually a function of the inputs as well. So we anticipate that if we added the input axis, if we could, we'd get a smooth curve here. We can see that the majority of simulations are at lower fidelities. There are a number of hyperparameters within the algorithm. We anticipate that potentially changing these hyperparameters to encourage higher fidelity simulations might help, or perhaps this is a function of our case study, a property of our case study, that we can learn about a high fidelity simulation from the low ones. So there's a huge host of things that we could do here as well. Okay, so actually the optimal reactor, this is, I think, is the interesting part to end on, really. Here is the reactor on the left, optimized with that basic parameterization I showed at the start, jointly with our operating conditions. So we're optimizing our 6 parameters here. We find that it does contain an inversion, and we investigate the specific fluid effects and what we think is happening within this optimal solution. We then 3D printed this. It's probably this big, yeah. And we performed the residence time distribution experiments, and we showed that while we can't validate the optimality itself, we can validate that the residence time distribution matches up our simulation. Okay, so that is our basic parameterization. Where it starts to get interesting is the results of these extended parameterizations. So these were optimized under steady flow conditions. On the top left, we have our basic coil. On the top right, we're optimizing the cross-section as we go along the reactor. At the bottom left, we're optimizing the coil path. And then with this bottom right reactor, I fixed the optimal coil path and then optimized the cross-section. So this is a kind of heuristic solution to this joint parameterization where I fixed the first set of parameters here. And so we identified a number of insights from these configurations, namely that the expansions and the contractions combined with a sort of horizontal pinch in the cross-section encouraged radial mixing. So you can kind of see that the black streamlines here that I've plotted on the outside are being curved towards the center of the reactor here. So slow-moving fluid is being mixed towards the center, and the blue streamlines at the center of the reactor are kind of being forced outwards to the boundary layer. There are a number of other insights here. Something that we identify, which I think is interesting, is that we can see the formation of Dean's vortices within our optimal reactor under steady flow conditions, and these vortices aren't present in a standard coil under the same conditions. So we're inducing behavior that we could only achieve with pulse flow operation through the geometry here. So we took those insights that we generated for these kind of, I'll call them small coils, and we took those and we generated a number of solutions where we're including the features that we identify in some final reactors. So these are actually currently being 3D printed. Unfortunately, I can't show any results. I can't speculate whether they would be better or worse. I hope they would be better. But this is where we end. So to conclude, I've specified a black box, effectively, which includes custom meshing code, which allows us to mesh simulations with 2 continuous independent fidelity parameters and a number of different flexible parameterizations. And I've specified a solution approach which takes advantage of multiple simulation fidelities to solve this expensive black box problem. And we've discovered some insights into the optimal solutions, and we've extrapolated those insights into a final design. So we have some preprints. So the first preprint is really focused on the fluid dynamics. This was done by Norshin, investigating the operating conditions and really digging deep into the physics there. And we have some more here. And all our code is available on GitHub. We'll be tidying that up as well soon. So thank you very much for listening. And yeah, thank you.